Okay, welcome to the second half of the 7th class. In the first half, we kind of went over, I guess, in a very sequential manner from the beginning to the Okay, welcome to the second half of the 7th class, where the first half we started the review process. I want to review everything from the beginning, from lecture 1, which is very conceptual, to this lecture 2 and 3, which is about the primitives of mathematical programming, capabilities, ecosystem, and whatnot. And we went through a lot of interactive visualization capabilities, and I emphasized in the first half that interactive visualization is not just it's not just a nice to have, it's not just a marketing gimmick, but sometimes because we are trying to communicate very technical ideas and lots of time to non-technical people, visualization of the data, visualization of how your method of analysis works, visualization of the results of your data analytics, of your analysis, a visualization of how the results would translate into insight for business or whatever. And that's very important. So interactive visualization is extremely important, and it's not a trivial exercise at all. Right. Now, we're on to the second and third pillar of data analytics, right? And that's the probabilistic modeling and statistical inference and machine learning based data analytics. And as I said many times, that it's your responsibility to have gone through fairly complete, I guess, useful or usable understanding of probability models and statistical inference. So in this class, technique-wise, no, we won't talk too much about it, but certainly as part of your project, you'll be expected to not just pay lip service to probabilistic modeling, but try to see if it has a place. Remember, if the data generation process itself, okay, has mechanism or has reason for it to be distributed in certain way, like normally distributed or binomial or beta distribution or gamma distribution, then using probabilistic models, probabilistic distribution to capture how your data is distributed is the right way to go. After all, it is more powerful in a way, right? You can make a lot of conclusion than machine learning based algorithm, right? If you can establish that your data has distribution this and that, say it's a gamma distribution with alpha equal to this, beta equal to that, then you can make very detailed inference, like p-value, probability of data falling within this range, some kind of hypothesis testing. You can do all kind of powerful analysis, right? So don't give that up just because you're learning, unsupervised learning, supervised learning tools. It's when the data comes in a peculiar form that cannot be captured by traditional statistic that you would definitely have to use machine learning algorithm to crack. Okay, but it shouldn't be your first instinct. Okay, you get a data set, your first instinct should be maybe to run through traditional statistical tests, like a test for normality or something like that, Sharp-Burra normality test with time series, you do Durbin Watson, all kind of stuff. there are standard statistical probabilistic modeling tools that you should think of applying to them first. Okay, your instinct shouldn't be, hey, I got a new data set, let's build a neural network or gradient boosted tree. That shouldn't be your instinct. Okay, having said that, again, I'm not going to cover a lot of probabilistic model in that detail. It is, however, in the range of Mathematica has the most robust probability distribution library, even bigger than R. So that's not for nothing. R is always been thought of as the powerhouse. Anyway, so the idea of looking at the data, right? Identifying what kind of support, right? This is something that maybe I can ask you in the exam in the descriptive section, right? Because you are certainly expected to know the difference between random variable that has a discrete support, finite discrete support, or versus countable or infinite but countable, like the number of accidents that can happen anywhere on Earth. Well, it doesn't go to infinite, but it certainly has no upper limit, right? So it can be for the next hour, there could be no fire. It can be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, up to infinity. Now, the probability of having infinitely many fires on Earth is going to be 0, vanishingly small. But the point is you can't put a limit on it. So that's why it's infinite. Okay, you can't say the Earth can only have 10,000 fire in the next hour and no more. Okay, you can't say that. Okay, even though the probability is virtually 0. Okay, so that would be something like a countable or discrete support, right? The value can be integer. All right, it can be negative integer in some case. A lot of times it's just positive integer. Counting events, for example. Bounded continuous support, like uniform distribution, beta distribution. Semi-bounded, that means start at 0, right? Unbounded, well, you can think of unbounded as continuous value being positive or negative. So, for example, if you think of stock price, now stock price is actually discrete because you work to the final cent is 1/100th of a dollar, right? So it's discrete, but nobody used discrete distribution to model stock price. Now, what do you think would be stock price? Would it have semi-bounded continuous support or unbounded? Well, stock at worst can be 0, right? It can be worthless. It can't be negative. Okay, so it has to be semi-bounded or continuous support. Now the return can be negative, so that's unbounded or continuous support, has negative, positive. So this 4 area, you certainly it's like that question I will ask you about numerical scale. It's one of those things where you have to be aware first of what your data looks like. Okay, so I can ask you qualitative statement like I'm interested in height of a mongoose in South America, okay? And I want to find a distribution. Now, what would I look to? Would I look in finite discrete support, or would I look to unbounded, semi-bounded, and so forth, right? Is there an upper limit on the height of the mongoose in South American forest? I don't know, okay? If you can't say it, then it's infinite, even though you know that it's not going to be infinitely tall, but the point is you don't know how tall it is. Or if you're willing to say, well, cannot be bigger than 5 meters, then you can make a hard limit on there. Okay, fine. Yeah, sometimes it's a choice, by the way. It's not always clear, but you have a reason, and you can state that reason. And these are all the. I think I may have mentioned that, even though I was not the one who taught you probability. I did mention, I guess, that in life, if you know about 10 different families of probability distribution, you're good. You're good. And these are pretty much all of them, I think. Okay. So Bernoulli, binomial, right? Normal, all this you can go through them line by line. There's some. This function is sort of like my function for giving the summary. That's all. All it does is just to say, give me the name of the distribution and I'll show you what expectation for the variance is. It's not that interesting. So I'll say, okay, this is binomial distribution, right? Binomial distribution. How does it come about? It's counting number of hits when you have n number of trials. Okay, so you know, you can toss a coin 10 times, and each time the coin has probability of 0.5, right? So how many hits can you have? Well, that number should be like binomial distribution. Or you can ask a friend to your party, and every one of your friend has a probability 0.2 of saying yes, right? And you ask 100 people, and you can find out the distribution of the number of people who show up at your party, right? That we n is equal to 100 and p is equal to 0.2, right? So forth, right? So if you ask 100, each of them has 0.2. So what's the mean? NP, 100 times 0.2, 20. Okay, that's minus, right? Bernoulli distribution, and sometimes now this is where you should start to actually inspect the details of manipulate, because a lot of time, you know, the main action happens only in one line. Okay, in this case, it's a discrete plot. Okay, of something, of a view of what do you mean by view? Well, view is a choice. I can do PDF or I can do CDF. Okay, fine. So it's a discrete plot of either PDF or CDF of a binomial distribution. So I've got no choice in that, but I have choice in terms of n and p, right? N and p. So that's the main action line. Now in manipulate, there's at some point there'll be a comma, right? And there'll be all these buttons. So N is a button, there it is. P is a button, there it is. View is a button, there it is, right? And there's also S bar chart or not. Okay, so all these are options, but the main action is right here. This is one action. There's usually just one action, the visualization something. Okay, and so everything else just give optionality or some kind of window dressing, certainly, right? If I view as a CDF, I want extend marker to be filled or empty, or okay, this is something that I just make it up. Okay, so as a bar chart, you know, so these are all pretty well. Again, visualization is not just about being pretty, but certainly giving intuition. So all these are, you know, formatting and appearance and all that, but really just one line. Okay, one line. So get used to this thing where you see a code like from demonstration program, right? And you just glass through and say, okay, where's the action? Okay, the action is here. Start from here. Okay, start from the action line, find the action line, go from left to right and see all the options you have and see all the formatting or appearance. Okay, like extend size to the right, view to the bottom, control plane, like that, all kind of stuff. So play with that, play around with that. So all this is this is something I like actually to show you. It's not that important, but most of the time, you know, the normal distribution has this kind of shape. Okay, that's kind of Napoleon's hat shape. Okay, you don't know how it came about. So what I did was I start from x squared, e to the x squared, e to the minus x squared, and that's basically what the shape comes in. So I did kind of a, you know, construction. So this gives a good intuition. A lot of time, you know, I would bet that even when you're taking probability distribution class, when you go to normal distribution, either you don't see the formula or you're told to just say, okay, that's the formula, just deal with it. Okay, but this is actually a very intuitive way. You say, okay, well, let's start with plotting x squared. Okay, well, how about exponential of x squared? Okay, so for exponential of minus x squared, I do that a lot. So this is to show again, and this is something you can't do in other language, but in mathematics you can say integrate from minus infinity to plus infinity of this function. And of course, by definition, you knew what's going to come up to, right? because this is actually the definition of a normal distribution PDF. It has to integrate from minus infinity to infinity, right? And that infinity to minus infinity to plus infinity has to come down to 1. Okay. Now, this is even more interesting. It doesn't give you 1. It gives you this. Why do you think it doesn't just give you 1? Because there's a constraint, right? I can't just put any sigma square. The real part, well, it's a little bit too technical, but the point is sigma square has to be non-zero. Okay, has to be non-zero, has to be positive, in fact. Okay, but in this case, the real part, if you talk about just this, it has to be positive. So if this is positive and it's equal to 1, that becomes 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 1. If this is 5, that becomes 25. 25 square root is 5, 5, 5. So everything cancels out. So everything comes to 1. And you can do this, understanding quantile. Now, if I were to ask anything from you at all, from probability distribution class, I'm not going to ask about hypothesis testing or confidence interval, because that's a little bit really specific to statistical inference. But there are 2 concepts from, well, actually 1 concept, but 2 things I can ask. From probability, classical probability that should be on the top. You should have that for the rest of your life because it's going to be useful in data analytics. Doesn't matter if you go to neural network, it doesn't matter. You're going to have to understand this concept, and that is quantile and p-value. Okay, they actually the same concept, but in different contexts. Quantile and p-values. If you don't get this concept down, your life is going to be very difficult. So I'm going to ask some quantitative, maybe interpret about what's a quantile of this. I'll give you a distribution, maybe something. Okay, so quantile and p-value. So this okay, I'll go to multivariate distribution just to look at things maybe a little bit. You know about this, right? This is a nice one I just added. You guys have well, if you're not from financial or economics background, that's understandable. But this is what happens. When you go to probability distribution class, they'll tell you everything in life has normal distribution. Then when you go to financial econometrics or financial economics class, they'll tell you that's a lie. Everything is heavy tail, or at least student's T. Okay. That concept of heavy tailness is what I was trying to elaborate here. So normal distribution looks like this. Bivariate student T's looks like this. The difference is that basically what happened is that the middle portion. Let me draw a picture. Okay. Now this is in 2 dimensions, but you can see that in 1 dimension, this is in the normal distribution. Maybe the normal distribution. Okay. How would I draw student T distribution? What do you think? How? It would look a little bit like this. It would look a little bit like this. However, it's kind of like going to be something like this. Okay, I'm exaggerating. So the word heavy tail is actually misleading. It's not just heavier tail, it's also peakier. What it means is that if this is a normal distribution, think of this as return from the market. Which one scares you more? Let's put it this way. Which one should scare you more? Blue or green? Green should scare you more. Because a lot of time, it's not doing anything. You're happy, you think it's stable, and then boom, it goes over there, right? So the green is what they mean by heavy tailness. Well, the difference is that everything has to integrate to 1. So you just can't have this thing bigger everywhere. So what happened is that it's the middle portion where the student T is smaller. So if you take the blue line minus the green line, you get something that sticks sort of like in the donut area here. right? And everything else be below zero. Okay. So that's what it means. High market. Distribution that's not logistic but has similar peakiness. So in real life you will realize that financial market tends to be like this. Okay, I don't know if you've seen those kind of funny hats that I think very old traditional Chinese hat, I think looks a little bit like that. I don't know. Anyway, so it's like a market. It's seducing you. Say, oh, the market is fairly stable. Most of the time doesn't move much, and then it goes a lot. All right, but it goes up as well, and then you get excited, and then it goes a lot south. Then you get really sad. So that's the distribution view. This is something I'm not going to talk about here. This is the one thing that I actually invented. Just a sidetrack I kind of like. And I'd like to show this very much because I actually have a typo in there that I haven't corrected. But if you go to here, now I want to show you this because of one thing. I did mention to you. Right. Basically, this paper just comes up with some function. It has to do with risk. And this is what banking risk is all about. But anyway, at some point, I have to integrate this function. Okay. And if I were to give this to MATLAB, it can only do it numerically, meaning I have to actually give real value and it will give you some function. Now, I can try to do this using my brilliant mind, but I guarantee you I didn't have a brilliant mind, so I would never be able to integrate this. Fortunately, Mathematica understand that this is a function, and it actually involved this confluent hypogeometric function of the first kind. I have no idea what it was. That was the first time I saw it in my real life. And this is what the integrated comes down to with this factor. And this is actually an integrand that involves infinite series. Okay. So actually, this ended up being the function. It has a gamma function on the bottom, has a Hummer function, blah, blah, blah. I don't like to show this very much again because I just have the PDF version and I had a typo and I haven't corrected. But that was the power. I actually forced integration because when you come up with any kind of new distribution, all you have to make sure is that it doesn't go to infinite and it integrates to some finite number, and you use that as a normalization. So that's why integration comes in. And economists have to do this because, if you're going to present results in economic journal, empirical research are kind of interesting, but it's not as, let's say, it's not as prestigious as if you had analytical results. That's I'm going to skip over that. So skip over this copula. Don't need that. But Mathematica has this copula function. It's called copula distribution. Blah, blah, blah. Inferential statistic. Again, I'm not going to talk too much about it, except, here we talk about our good friend, Old Faithful Data. This is Gaussian mixture, right? It's actually a mixture of two normal distribution. That's a data, that's a fit, and so forth. And you can see that it's got pretty good fit. Okay. Now, keep this picture in mind. This is done purely as a statistic problem. Okay, keep this in mind because I'll actually mention this problem again when we go to cluster analysis. Now, the main part. So this is the hard part now. This is the totally new thing that you guys learned. This is applying unsupervised machine learning to data analytics. So data analytics with machine learning. After the break, after the midterm break, we'll come back to supervised learning, right? But this one, unsupervised learning. So I have concept. This thing I haven't put text, but this would be in the mind map, right? What's machine learning? Again, concept is a machine is something that's supposed to do some task. And what's learning? Well, learning is a task that you do. And what's the difference between a machine learning and say statistics? Well, statistics is sort of like you have a function and you make the test. And if you think it fits, then you fit the parameters and so forth. Well, with machine learning, it's kind of two stages. One thing is to say, I let an algorithm learn about the data. So that's the task, right? A machine has to do some task. But having learned that, it's not yet useful. It's only useful because you're using it. So when you do some kind of regression, right? Y is a function of X. Well, the machine has to learn the relationship between X and Y. That's task number one. Then task number two is to make prediction. So with machine learning, there's always two jobs. A machine always performs two tasks. One is useless. It has to learn first. That's task number one. Number two, once it has learned, then it can make prediction, it can make conclusion, it can make inference, it can make clustering, it can make all kinds of stuff, right? So it does two jobs. So it's sort of like a machine that cannot work yet. Before it starts to work, it has to see a certain set of data. Once it's seen a set of data, then it understands the problem, then it works for you. So it's always it's got two jobs. One's a learning job, one is the sort of like inference or prediction job. Again, there are many machine learning paradigm. Primarily, the three top one that you will see in any textbook is unsupervised, supervised, and reinforcement. There's also semi-supervised, which is a kind of catch-all for something that has been happening in the last 5 to 10 years in the machine learning community. Anyway, these two are not covered, right? This one is covered before the midterm. This one is covered after the midterm. Right. All of this, again, go click. There's also a guide. There's a reference, cluster analysis. Go read them. Okay, go read them. Right. So there are, roughly speaking, two family, right? So I can ask you that, and you should be able to tell me right away. The two types of cluster analysis. One is based on distance, right? Distance. The other one is based on density. So how does this work? Again, you can give descriptive explanation of the algorithm. For example, what's a DB scan? DB scan is you start with some data point and you try to link up the data points that can be reached within certain small distance. And if you can reach all of them, you consider that to be one cluster, right? Those that are not reachable would be another cluster, right? On the other hand, if you try to find like a cluster center, okay, and then you try to find the points that are close to the cluster, and then you move the cluster to be in the middle or the central, the mean of the cluster member, and then you keep doing this until you stop. That'd be like k-means, right? So if you understand basically k-means clustering, how it works, DB scan, you're good, okay? Other things are similar in understanding. Hierarchical is a little bit more elaborate. It's actually a very elegant way of thinking, but I think the easiest thing to understand under the hood. I just want you to, as a user of supervised of clustering analysis, you have to understand distance based versus clustering density based. Okay, and for that you just need to pick one of each. Okay, dB scan and k-means. Okay. So read about that. You can, by the way, there's like 1,000 YouTube videos on how k-means work or something, how simplify, and they do like animation much better than I could do with my hand. So I suggest you go to that. Okay. Now, this is some various demonstrations. So I can just say that because again, as a high level language, it's understanding what it means to be a data. This data happen to be a color, so it actually can do clustering analysis on color. Now, visually, you can tell yourself, right, that this is one cluster. This cluster you will call, it's kind of like light greenish. This cluster you would call maybe sort of like bluish. This is red, this is more magenta, and this is kind of orange cluster, and this is kind of like meh, you know, just brown. So that would be something like a cluster. Okay. Now, yeah, you can also, you know, see that hierarchical clustering with dendrogram. You can see how it's sort of like when you were kids. You remember you have like color pencil. You guys remember that? It doesn't actually order that nicely, neatly. Sometimes you have to, you know, but this is what essentially it does. Okay, you can imagine that if I have 100 color pencil, and I want to order it in a nice order from left to right, that's what this dendrogram is going to do. So it's kind of based on similarity in color and hue and strength. So go from light yellow to green to darkish blue, darkish red, and okay. So it's basically the intuition behind it. Anyway, now the demonstration I want you to pay attention to is the one we went through so many times, right? The old faithful data, right? So this is example data. So let's look at that. So in one line, I import, right? I give it the name, I list plot it, and I don't want a big picture. So these are the two modes of application, and I want you to understand these two things, right? If I wanted to be cluster once, how do I do it? Just find cluster, right? Do it once, find cluster. Use this function, find cluster. Okay. Now, if I don't want to do it once, but I want to have a function that would then separate cluster 1, 2, 3, and then if I have a new point, I can test what it is, then I would use this thing called cluster classify. So these are two different modes, okay? Dendrogram, okay, we talked about that. And this is the one that we play a lot, so I'm not going to go over that again. Now, I tend to do this a lot as well. Just as I have module within a function to have localized variable, I also use manipulate with module. Okay, so I have localized variable here. So these are things you can play with, and so forth. So for example, let's say I generate some data set. Now in this case, I happen to generate it like this. Then I name this thing. Now this is not in the module because I want it to be available outside. So this becomes a data set that I can play with, and I can do this kind of thing, and you know, do kind of find cluster, right? The two cluster or so forth, and all kind of stuff. Oops, oh, I haven't run the full cluster. So these are two. This one is obviously going to be a little bit trickier than that one. That one just has two cluster. This one has 4 cluster, and I ask you to play with this in one homework, right? So that if what you would have been nice. All I wanted from that homework was something like this. Originally, if I did this, then it does come out. Okay, with 3 cluster. If I stretch this apart, okay, then it's going to have 4 clusters. If I move them together, even though I generated them using 3 different lumps, the cluster analysis is not going to be able to identify them. So it's going to find like 1 cluster, something like that. That's all I wanted you to make the conclusion, because you were God, right? You created this from 4 lumps of data. So you knew that in a way there are 4 lumps, there should be 4 clusters. But if the 4 clusters are so close together, what can you expect from the algorithm? It's not going to know that, right? It's not going to read your mind. So it's going to look at this and say, yeah, that's just 1 cluster. That's just 1 cluster, right? That's the lesson I wanted you to learn. So say in real life, because you are not God, you did not generate the data cluster from 4 different lumps. Okay, you just get the result. There's no way to tell. Okay, so you have to have some kind of criteria of data that, you know, it separates well between cluster. It's very close within cluster, but 2 clusters are far apart, that sort of thing. So this is where we summarize data analytics into a pipeline, right? It's to say that, okay, well, what are the steps, right? Find the cluster, blah, 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 and then make the conclusion here. So I encapsulate. Now, this is the flavor that the sort of style that you would end up doing. Now, I want to show you this because this is how professional data scientists would probably follow through. There'll be like a lot of trial and error here, just one liner to do things here. So this, okay, even though I just wrote it like this, like I know exactly what to do. In real life, you try so many things around here. So this is sort of like your experimentation. Okay, try this, try find cluster, try this, try plot, try this, try that, try this, try that. Let's say once you're happy with all this step, all the way from pre-processing to running the algorithm to visualizing, once you're happy with all the steps, then you encapsulate it as a set of function. So this becomes something that, you know, you deliver to your client or to your deployment team, whatever. Okay, so you encapsulate. Once you're happy with the step, all that, okay, let's wrap everything all up in one function. This function is called prepare data for the cluster analysis. Okay, I'm happy with that. So I prepare the data. This is a second step. This wrap thing called cluster analysis on cluster analyzed data that's already standardized. Okay, so this assumes that the data is already analyzed, standardized. So you go from here to here, and then you visualize, right? So this 3-step becomes 3 functions. 3-step become 3 functions. Okay. Now let me take a segue a little bit. The example that I gave you, okay, the example I gave you, I gave you the version that I told you not to do, which is once you cluster the data, do dimensionality reduction per cluster. That's what I didn't want you to do. But it turns out when I checked that that's the version I gave you. What it should do is this. Do the dimension reducer on the entire thing. Okay. This is what I mean by flatten one. And this is a bit of detail. Okay. You can track through this, but the result of the cluster analysis looks a little bit like this. Okay, let's say you have 3 clusters. You have 3 clusters, right? So this is the result. Okay, you have to look at the board. So this is 3 clusters. This is data point, data point, data point. Okay, now if I did this, if I do this, if I did find cluster, do what's going to happen? It's going to find cluster. Find cluster. Okay, dimension reduce. It's going to go through this. It's going to reduce dimension, all of this. It's going to reduce dimension in all of this, but it's going to do them separately, right? It's going to do them separately. So you're going to lose the fact that these are supposed to be far apart. So what you should do instead is find a dimension reduction function that applies to all of this. Now, how do I apply to all of this? I have to remove this bracket. And that's what this flatten does. It removes a bracket, but doesn't go away there, because when you go down there, that's higher dimension. So it's a little bit of tricky programming, which is so that's the only tricky bit I have. Okay, the tricky bit I think is this bit is a little bit hard to understand. So this is basically a list of a list of a list, right? The first list, just everything. The second is listing cluster. The third one is if that data point is in 5 dimensions, then you have a list of 5 numbers. Okay, I don't want to flatten all the way to those 5 numbers because they are distinct. So I want to flatten to just one layer. So that's why this is a function called flatten, comma 1. So to read and to understand this, go to this. There's a good example. Okay, this is a flatten function. See that? This is all the nested bracketing, all the list. If I do flatten, okay, if I do flatten all level, it's gonna do this. A, B, C, D, E, F, G, H, right? Flatten everything. So remove all the bracket. Okay, just flatten everything. But if I flatten only at level 1, okay, so I go to this level. So that's why it doesn't flatten this guy. This will be level 2. Okay. Now you can imagine that this is exactly my situation. I have a list of clusters and I want to merge the clusters together, but I don't want to flatten all the way down to the first bracket because that's multi-dimension, right? So what I want to do is just flatten 1 to level 1. And this is, I admit, this is a little bit tricky to understand. Okay, that's all, but everything else is easy. Okay, so what I did was, okay, and you can follow this. You can follow this. Follow this. Visualize the result of cluster analysis. So this is assuming I have a cluster analysis. I'm just going to visualize it. Give me some name so I can give some name. Okay. So the line thickness is my way of having the width of the line. Now this 0.1 is just there because I tried different value and it's too big, it's too small. So I just 0.1 looks good. Just take the cluster analysis, divide by total. So that gives you the length, right? So the number, and this, you can go back, read here. Use length to find, use length to find out how many members each cluster has. That becomes the cluster size. Use this cluster size to define the line thickness. So all this is explained with some word up there, but down here it's not explained. So basically I have thickness of each cluster, right? Because I'm going to look at all the cluster, each cluster, I'm going to find out how thick the line is. That thickness represent the number of elements. So if I have this class into 2 clusters and that cluster has 10 people, this cluster has 5, I want to use the line that's twice as thick for those people and one line that's half as thick for these people. Okay, so and dimension reducer. So this is the one that is say, okay, reduce everything down to lower dimension. Okay, and this is going to be applied to what's our data set. Okay, let's do them together now. So right, so now this is my data table, right? This is my table. Boom, done. Okay, what is this? this is looking at the data of COVID. Okay. I'm going to use just this column. I chose arbitrarily, but this is one I chose. So there are actually 28 dimensions. There are 242 locations. So maybe like 237 countries with continents and the world. Okay. And I do the preparation, and this preparation, all it does is standardize. So let's do that. So anyway, so once I've done that, yeah. So this is all the function. So I have to, it's blue, so I have to make it shift enter. So now the function works. This function works. This function works. Okay, all right. Now, so imagine that I just turn on the machine. I make all the blue one. I shift enter all the blue one, so the function works. Now I'm going to use it. So what's going to happen? I'm going to import this data set. Okay, we just did that. Sorry, did it again. So this is data set. Okay, I send it to this function. I send it to this function. This function, which is this function, send it to this function, which is to prepare. Yeah. Sorry, 1, 3. This 55. Oh, yeah. The dimensions just count the length, right? But if it's a matrix, then it gives 2 lengths. So, okay. So if I have something like this, 1, 2, 3, okay. And, okay. What's dimension it is? 3, right? But if it's 3 by 2, let's say 1, 2, 3, and then another 1, 2, 3, and then bracket, right? So this is 2 rows of 3 columns. So this is 2 rows and 3 columns, right? 2 rows, 3 columns. So basically, this is the length of this, and this is the length of the second layer. Yeah, okay. Yeah, this is maybe, I don't know if it's a bad habit, but I tend to do this a lot. This is my data import. Okay. Once I import, I want to check the dimension. But instead of writing in a separate line, I just put a bracket around it and put dimension. So I do it one shot. So I do it 2 functions. So I import, save it as data table, and I check the dimension. And it has 242 rows of 28 columns. Oh, here. Okay. Here. Because this data set, okay, why do you have 1, 2, 3, etc., 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 and 2, 2, 2, okay? Because if you look at the data set itself, this is just because of the data. Okay, so we are here. Look at this data. This is the one that I'm going to download for, right? Okay, so open it. Oops. Okay. Why is it not opening it? Something's weird. I don't know why. I shouldn't have problem with Excel. This machine has Excel. Let me put on desktop maybe. This has nothing to do with okay. For some reason, I think, okay. Now, this is the sheet, right? Now, Excel has row and column. CSV has row and column. Excel has sheet as well. So there's actually 3 index. So if you look at this one and say, why do I want this? Okay. Why do I say this? I put in 1 because I want the first sheet. I don't want the second sheet. Yeah. It's in the import. When you look at import Excel, it's well, think about it. It's common sense, right? How do you access a number in Excel? You have to access the page. So this one, see, there are 3 numbers, 1, 2, and 3, right? So what does the first refer to? Well, common sense would say the first is the number of sheet. So 1 means the first sheet. So if I put in 2 here, what would it go to? It will go to here, right? Okay. If it goes to, if I put 3, it's going to give error because there are only 2 sheets. So 1, okay, 1, sheet number 1. Okay. So what's the next number? Next number refer to the row, correct? Now, I happen to have something here that is not relevant. So I don't want the first row. I don't want the second row. I just want the third row all the way down. Now, this is where you actually have to look at your data. This is specific to your data set. So a lot of time you have to talk to your data supplier, okay? But you can visualize it. Usually there's like a README page that describes. So basically the data begins in third row. So sheet number 1, third row down, third row down. Okay, which column? Well, I actually don't want the color. I don't want the name for some reason. I don't know why I didn't want it. Oh, I just didn't want it. I just want the data. I don't want the name. So I go to. Why don't I want the data? I think the name I save it separately, I think. Okay, it just happened to be the way I work. Maybe I can download from the first one, but this case I just want this all the way. So second column, first sheet, third row down, second column to the right. So that's what this guy does. Now, once I've done this, I have to start count from 3, 5, 9, 10. So 1, 2, 3 total case per million, 4, 5. Now, there are more elegant way of doing this. In real life, remember that dictionary that I told you? That's the one I'm going to use, the data frame, because that's going to allow me to refer column by names. In this case, I don't want to bother creating a data set. So I just happen to pick, I want total case per million. I want reproduction rate. I want this. I want that. So I know that it's a third column. It's a fifth column. It's a seventh column, just for this example. Okay. So for this example, I just happen to do that. Now, in real life, you would actually build a data frame and then you would choose, okay? So all it does is to say, I have 242 country or continents, and I have 28 numbers, which is higher than 2, higher than 3. So I can't see it. I can't see it. That's why I want to play with it, okay? Now, I'm going to analyze, visualize data cluster. This function is this function. This function calls 3 functions in succession: prepare data, cluster, analyze, visualize. This is what I mean by encapsulation. Okay. So this is not something that you need to know as a student, but I want to show you how you would work, as a professional. Okay. So how you would do it as a student is step by step up here. Yeah, step by step. Once you're happy with the step, you wrap it, you package it. Okay, so you package it 2 stages. One, you package all the data preparation into one function, package the analysis in one function, and package the visualization into one function, and package the whole thing into one function. Okay. Why do I do this? This is called modular design. Because if I wrap everything in one function, then it's not clear which one is visualization, which one is that, okay? If I don't have the whole wrapper here, I can just give the 3 functions to the clients. That's done, but then they'll have to call them in succession, right? So I just make it, yeah. Now, this is what I mean by modular design. In the future, in fact, imagine that the one that I sent to you last week was version 1. What I changed was I changed this bit. I change a component. Do I have to change this? No, it's modular, it's plugin. So I just redefine this function and then you're good to go. So you don't have to copy the whole sheet. I will just give you this because this is the one that I changed from last week. I give you this and then you put it where the old thing was. And now it calls three things. So what does it do? It sends this with the column index. Oh yeah, I know why I didn't want the column name because it's 28 of them. I'm never going to look at them anyway. Right. So this is what I did. Oh, I did look at the name. Yeah, I did have the name. I don't know why. Now, remember the version I gave you was to do dimension reduction for each cluster. Turns out that depending on how you cluster things, you're going to get different results. So when you go down here, okay, there are many ways of clustering that I show down here. All this dimensionality reduction picture are going to be different. That's the one I said do not do. It's no good. It doesn't give you any insight. So I want you to have one dimension reduction that do dimensionality reduction for the whole data set. And the right answer, the right way to do it would be like this. So if I apply different, this is the what? This is the clustering algorithm. The clustering will be different. The clustering will be different, but the dimensionality reduction representation in 2D will be the same. But the cluster will be different. Why is that useful? Well, let's look at two cases. Let's say I have two cases here. See that? Based on the algorithm, it's doing cluster very differently. What's this guy? This guy is DB scan, right? DB scan is like within a close distance. Can you touch everybody? It turns out that everybody can be touched by this big chunk here. And this is what? This is the average for the entire population of that cluster. And how big is that cluster? Well, I don't have the number here, but certainly it is a big, right? So this is a thick line, right? You see how thick that line is? In this case, I ended up with two cluster based on 12 dimension. Okay. Now let's look at cluster 1. That's this guy. That's a special guy. Cluster 2 is this guy. Now the thickness doesn't matter because I just want to show the line. Okay. So now this versus this. Okay. No thickness. Now I put them together. I represent relative thickness. So there's a big population of average. And there's like a small number of countries that really has high population density. Okay. High population density, right? And yeah, because I only keep the name of the variable, I didn't keep the name of the country. I don't know what country is. I didn't keep track anymore. But this is a country that has high population density and high number of hospital beds. You know, my guess is Japan, but okay, because it also has old age, I think. Oh yeah, so aging society, lots of bed. Yeah, I'm guessing Japan. Okay, but I didn't keep the name. So. Right. Based on this, I'm gonna do visualization of these 12 dimensions in 2 dimensions, 2 artificial dimensions. This is it. So as you can see, it doesn't separate really well. Okay, it doesn't really separate really well. It's kind of like, yeah, but in this case, you can't really see very much, but certainly it kind of overlap, but you can see the blue one. Now, this on the other hand, this is a little bit like k-means. Oh, we can do k-means. K-means is here, I think. Yeah. With k-means, definitely it's going to have kind of like even number of cluster, because even though you can touch each other, the point is that originally you already set to belong to different cluster centroid. So this is going to have many cluster. cluster 1, that's cluster 2, that's cluster 3, cluster 4, cluster 5, right? And let's view them all. Okay. Now, here you're beginning to see that it's more like a distance, but in terms of distance, because after all, dimensionality reduction is kind of distance based. So you can see that the blue is kind of here. The green's kind of here. The orange is kind of here. In fact, let's look at one by one. Yeah, this guy's over here. This is one cluster, right? Now, this one cluster, the mean of this guy in 12 dimension. So they both are abstraction. You're not looking individual data. You're looking at the mean of the cluster, but you look at all 12 dimension. In this case, you look at individual member, but you can't look at original dimension. You look at 2 artificial dimension. Okay. So they both give incomplete picture. Anyway, so this is this guy, the blue, this guy. Now let's go to somebody else. This is another guy's over here. Right? Now, obviously everything, because I look at them one by one, I didn't bother with the color. So it's all blue. But if I look at all of them, it's going to have different colors. So the purples are here, the blues are here, the greens are kind of here in the middle, orange is a little bit to the right. Same here, right? So these are all different clusters. Now, they have different clustering criteria, so they have different clustering result again. And this is where the art comes in. You don't necessarily have the one right way of clustering analysis. All right. So this is Gaussian mixture. Okay. There's this one called neighborhood contraction. Neighborhood contraction kind of like try to shrink things together. So it actually shrank everything so well that there's only one cluster. So this one's not very useful. Okay. This one. Now, this cluster centroid is actually how I use things professionally. Okay. So in a high dimension, you can't see original dimension for all data. So this is sort of like all dimension, but not all data, just a representation of the centroid cluster. Okay, the cluster centroid. So the average of all the elements within the centroid with the thickness proportion. So obviously it's more here, not so much here, not so much here. So this guy will have a lot of members, see a lot of blue. The green, very few greens, right? So the thickness is proportional to the number, obviously. So that's this. Now, I kind of like I'm struggling a little bit of how to present this because the program here has dimensionality reduction, but I want to show it even before I talk about dimensionality reduction. So technically, you should be able to just read this. You should read just this. Okay? Look at this. That's all you understand. Come down here, read dimensionality reduction, go up there and view dimensionality reduction. Okay? Right. So now, dimensionality reduction. Okay, there's also Ph.D, but PCA, and there's so many things. And this is where this is real data, right? This is real data. I also have one on demonstrated data, and we did that. We did this kind of Gaussian kind of, remember that kind of thing? We did that. So I'm not going to spend time on it, but go through that, right? So this is a little bit like the earlier problem where if you generated it by hand, you kind of know, okay? And these are the 3 things I told you, right? Don't do this. Don't do this. Don't do dimensionality reduction on individual cluster. This one, you do dimensionality reduction first and then clustering. I don't recommend this, but there are occasions when this is useful. I'm going to spend 2 minutes talking about this versus that. Okay. Both dimensionality reduction both dimensionality reduction and cluster analysis represents a way of machine learning. It's learning some kind of feature, trying to find a pattern. Let's draw this in high dimension. Okay, let's say you have something in higher dimension, and you know, whatever, right? This is very hard to visualize that this cluster is blocking that cluster from your point of view. Okay, something like that. Now, imagine that you can't see this. Putting this down into this. Okay, so this is 3 dimensions, this is 2 dimensions. What do I recommend to do? I recommend you do clustering analysis first. Then do dimensionality reduction function on the whole thing. So that when you do this guy comes to here, this guy comes to here, and this guy comes to here, let's say. Right? And then you can visualize that there's some kind of separation in artificial dimension. Okay, so cluster first, then dimensionality reduce, but don't do it individual cluster. Get a dimensionality reduction on the whole data set and do it, but keep track of which cluster it belongs to. Okay, so the blue becomes a blue, red becomes a red, green becomes a green. So you keep the cluster name separate. Now, this is what I recommend. That's 0.3 or something. The 0.2, which I said is okay, but I do not recommend, is this. I have the original. I put them into 2D. Then I do cluster analysis. Okay. Why do I not recommend this? Two reasons. First of all, when I did this, I still have the option of looking at the centroid in original dimension, right? So I can do this cobweb, right? If I did this, what's my cobweb? It's 2 dimension and it's artificial dimension. So it has no meaning. That's number one reason. Number two, and this is a little bit more subtle reason. Number two, dimensionality reduction is kind of like distance based for most part. Whereas with clustering analysis, you have the option to do distance based and density based. Anyway, it's 2 different techniques. Okay. So if you do dimensionality reduction first and your dimensional reduction is distance based and you wanted to do density based, you kind of mess things up. Right? So what I want to do is do clustering in the original dimension, but only look at the result in the reduced dimension. If I want to look at individual data point, that's what I mean. Okay. So there are 2 reasons why this is better than that. Is there any reason why that is better than this? Some occasion when you don't care about the original meaning and the original dimension is so big, it's so sparse that the clustering algorithm will get lost. Remember I told you that if the dimension is too high and you send the algorithm to look at it and the data is kind of like maybe spread out, but maybe in certain direction more meaningful than the other, you don't want the clustering algorithm to get lost in high dimension. So you do dimensionality reduction first because you had 10,000 dimension. You reduce it to 30, then you feed it to the clustering analysis algorithm. Now, if you have 1,000 dimension, you're not going to be able to look at individual one anyway, right? Sometimes you do that. Give me an example why that would be the case. Well, when you work with genome data and things like that, you have so many high dimension, for example, I don't know, I'm not a genome expert, but things like that, where they're so high dimension that you can't really look at individual anyway. And if you want to interrogate individual gene, you will find out by data search or whatever, query or whatever. But it's such a high dimension that the cluster algorithm get lost. Basically, that's what I'm trying to say. Okay, that will be the case. But that would be something where you really get into an expert area. You have to know your data really well, and it's a problem. What's called sparsity. But anyway, for the purpose of this class, just take it as my recommendation that you should do them in this order. Okay, so do them in this way. This is generally recommended practice. Okay, this is not generally recommended. Doesn't mean that there isn't a use case. This one I don't recommend at all. Okay. Now, this here is combining what? Dimensionality reduction and cluster analysis, right? Both of them are unsupervised learning techniques. I use them together. Very useful, very powerful. Before I finish today, there's one more thing that I didn't cover. So far it's supposedly review. One thing that I didn't cover was that, cluster analysis can also be used with traditional probability and statistics. And this is very intuitive here. Okay. Now, let's go back to our old friend. What's our old friend? This guy, right? Old faithful data. Now, let's just look at one dimension. Okay. Let's look at that one. You can look at 2 dimensions, but let's look at this one dimension. Okay? And I can use hand waving if like. Now, if you have this distribution, right? And you ask Mathematica to find distribution. There's actually a function called find distribution. What it's going to do, it's going to give you mixture distribution, because it can do mixture distribution in 1 dimension. That's one reason I'm using 1 dimension. Okay. So what it's going to give you is this. It's going to give you something like, well, actually we can do this. This is already clustered. So, okay, before I cluster, okay. So I'm, oh, let's look at the second one. Sorry. There it is. So I'm looking at the second number. What's the second number? It's a waiting time, right? So I'm just looking at waiting time. Old faithful, all data point, second number is the waiting time. Find distribution. What's the result, guys? It gives you this. It's a mixture distribution or Pascal distribution. I don't know what that is. And binomial distribution. Okay. Now, with find distribution, you can actually do this. You can actually give it an argument. say 3. It's not going to give you the best fit. Why? Because the best fit sometimes gives you esoteric distribution like this. Okay. To some people, Pascal distribution is not esoteric. To a lot of users, Pascal distribution is esoteric. So let's give it a few try. Let's give it the top 5. So the second, the third one would not be as good. Okay. But yeah, maybe it's easier to understand. Well, this is not a good example because sometimes you go down, you get something like normal distribution. Anyway, the point is, it's going to say it's a mixture of 30% this distribution and 60% that distribution. Right? This is probability fit. Now, most algorithm like R or Python doesn't deal very well with mixture distribution. Doesn't deal very well with mixture distribution. In fact, Mathematica doesn't do mixture distribution in high dimension. But you know that it's multimodal. Okay? So that's a limitation of a traditional probability statistic. But you still like traditional probabilistic because once it gives you the component distribution, you can do a lot of, hypothesis testing and all kind of stuff. So how about this? How about, let's say, I know that it's multimodal, meaning the data itself has trimodal. Okay, trimodal. I know the data itself has trimodal. Okay, I can't fit a single distribution. With Mathematica, it's going to a mixture distribution. But let's say I don't have two. I don't have that too. Okay, let's say I'm working with, say, Python or something. I know that there are more than one. So what I'm going to do is this. I'm going to send this to a cluster analysis first. Okay. Once I send it to cluster analysis, it's going to do this. It's going to kind of put this thing in one cluster, put this thing in another cluster, put this thing in another cluster. Once you put them in separate cluster, you can. Oh. One time where you still want to use traditional probability statistic because you want this analytical form, normal distribution, Pascal distribution. Pascal is not all that exotic, but it certainly is a little bit more exotic. But you can certainly force this, right? And if you separate them into cluster and you test them and it doesn't fail normality, well, use normality, right? So this is one time where unsupervised learning is not a replacement for probability statistics, but it helps in situation where traditional probability statistics has limitation. And this is a very clever use of unsupervised learning. Okay. Again, I don't want you to, come to Basai, learn data science and deep learning and all that and say, whenever I see a data, I'm going to use a deep learning because I know how to use deep learning, right? Or whenever I see a data set, I'm going to use traditional normality, normal distribution because that's all I know. Okay. I've stopped learning more techniques since year 1. Neither of them are good. Okay, the general approach is to be what's called method agnostic. Agnostic comes from, like, if you don't believe in God, they call it agnostic. Well, this is the same thing. You don't believe in traditional probability and statistical inference. You don't believe in deep learning. You don't believe in decision tree. You don't believe in anything. You believe in trying them all and see which one's good. Okay, that's called method or model agnostic. That's what I want you to be. Okay, there are situations where you can prove that probability. Now, there's some. There's a little bit of hierarchy. If you can use normal distribution, use normal distribution. Okay, if you can't use normal distribution, you might have to do cluster analysis. In this case, this is one of those things where you can't use traditional probability distribution method, but by using unsupervised technique of clustering, you separate in one problem into 3 problems, each of which can be solved with traditional probability theory, probability model, right? So this is a hybrid, right? And if you are hell-bent on using unsupervised learning, you won't use it. If you're hell-bent on using probability theory only, you won't use it. But if you're my student, you are technique agnostic. You use combination, you use hybrid. Okay, you are open-minded. Okay, right. So, yeah, this is, remember this picture I showed you earlier? Well, earlier picture came from, fitting parametrically. Now, in fact, I kind of force it to be normal. I think I'm not quite sure, but I use mixture algorithm, right? But let's again assume that you're working with R or something, and mixture distribution somehow is not supported or whatever. Okay, and in any event, this is also a good approach, even though you know how to do mixture distribution. Now, if this were higher dimension, I would probably use it even within Mathematica, because I would do clustering first, and then I do the multivariate distribution fit. So, again, similar kind of picture, but arrived at very differently. Okay. Now, this problem happened to be trivial, so I know it's kind of like 2 normal humps. Okay, but in real life, it's not. So this technique is quite powerful if the technique above doesn't work. Okay, so even though the picture looks the same, conceptually very different. This is quite powerful. This is quite a cool thing to do, to be able to do. It's a hybrid way of doing. Now when we come back, we'll look at data. Supervised learning, and should be okay. Again, most time when you go to data analytics, they usually start the class with supervised learning, but I think I've made the right choice to go with unsupervised first. Okay, supervised learning is very intuitive. It's quick to conceptualize. Okay, and there are like many tools available. And in my life, I would say that most of the problem would use supervised learning as the main tool. Out of those, so second most, I've never used reinforcement learning in a consultancy project. I haven't had to use that. I use supervised learning a lot of time. I use unsupervising a lot of time. Maybe I use unsupervised learning a bit more for some reason, but for most people, supervised learning will be used a lot more. Having said that, unsupervised learning, just as you saw, it helps probability statistics. Unsupervised learning also helps supervised learning in many cases. Okay, so it's sort of like the problem is supervised learning. I want to predict Y from X, but before I predict Y from X, I want to do dimensionality reduction on X first. And that's unsupervised learning. Okay, there have been some problem when I did that. In fact, the project I did for asset management, looking at a lot of macroeconomic variable, Okay, certain variable, I want them by themselves, but certain variable represent like a global financial econometrics measure. There are like 1,000 of them. Okay, so I pick maybe 20 of them, and even that's too much. So I do dimensionality reduction just to get the first principal component of European market, first principal component of American market. And I use that for the Thai financial market analysis. So there is a problem of supervised learning where inside the data of variable are pre-processed with unsupervised learning. Okay, so unsupervised learning is a big deal. It's a big deal. Okay, now, so the exam, I guess, next week you should, you don't need, you know, aside from this thing that I can send you later. Okay, it's basically what you got already. So aside from that visualization that I said, I send you the one that didn't do dimensionality reduction the way I wanted to. Other than that, you know, you can use that for review for your exam. Okay, don't forget to go through the mind map first, though. Okay, make a narrative, make as if you're teaching. You just pick something random and teach your little brother or little sister. Okay, what would you say? What would you say about a heat map? What would you say about distribution, finding the distribution? What would you say about trying to predict y given x? What would you say the difference between classification problem and regression problem? Okay, what would you say to your friend who's from biology who knows classification is something else? You say, oh, well, in your world, my classification problem is identification problem. Okay, why? Okay, that sort of thing. Okay, so these are all conceptual. Review the YouTube if you like. All the YouTubes, all the class up to last class is up there already. So you can see them. Okay, sorry, we didn't have like a workshop time today, but you know, you don't need workshop time today. I think you need review, so I used the whole review. Next week again, when we go back to not next week, after exam, we'll go back to teaching, and I'll try to do that 1-1-1. You know, 1 hour of teaching, one more break, 1 hour of teaching, and then an hour of or maybe a bit less, 40 minutes of workshop time. Okay, you will have to use the exam. There's like an exam app where it kind of frees your screen. Like they'll work it out for you. Okay, so come here and, you know, sit in front, fill the front row first to the back, because the mentor, the proctor will sit in the back. You will have a thing, a notebook, even descriptive or text. You will write response in the notebook. So you turn in the notebook at the end. Okay, all the visualization, you can access the help file. Obviously, just press F1 anytime. Okay, good luck, and hopefully there's been it's gonna give you a good wrap up on what we taught so far. When we come back, supervised learning and project, and that's it. That'll take us to the end of the year. Okay, Cap, good luck. I might come in, drop by, just say hello or sneer at you or something. Okay, but definitely I'll see you in 2 weeks. Huh? อ้าวเหรอ Oh, อาทิตย์หน้ายังไม่สอบ Oh, sorry guys, I've just been told next week is not exam. It's the week after. How come I thought it next week is exam? Okay, so next week supervised learning. อ๋อเหรอ ผมไปเตะพี่น้อง